Okay guys, 8.3, and this is all about situations where we have constant acceleration. So when we know that a is constant, we can use calculus always, but we also have some set equations, we call them SUVAT equations, that can sometimes make life much easier. So here's our first question. Mr. O'Sullivan is arriving home. He decelerates uniformly, so with constant acceleration, and we know that his velocity as he enters this phase, so before he's slowing down, is 2 meters per second, and we know it takes him 4 meters to stop. The question is, how long does it take him to come to a halt? Pause the video, have a think, and start it again when you're ready to discuss. Okay, so best to think about this situation visually to begin with. Here's a velocity time graph. And we have Mr. O'Sullivan coming into this phase when t equals 0 with a velocity of 2 meters per second. And we know he stops. And we know that deceleration is constant. So constant gradient, he's going to stop. Our question is, well, how long does it take him in time? So what is this time? We know it takes him 4 meters to stop. And maybe the best thing to think about is that distance travelled is the area under a velocity time graph. So the area of this triangle has to be 4 meters per second. So then if I just use a little bit of geometry, I've got the area of the triangle, which is 4. So area is 4, and that's the same as a half base times height. So a half times 2t, which is the same as t. Therefore, the time is 4 seconds. It's a nice little proof just using the geometry and the idea that the area under a velocity time graph is the distance travelled. If we think about that for a second, we know that because if we integrate velocity, we get displacement, and so using the idea of calculus, the area under a velocity time graph is always going to be the distance. Now there is an equation that can help us here. The equation is one that connects all those elements we're talking about. And so what are we talking about here? Well, giving you a bit of a head start into how I want us to think about these ideas. In SUVAT, we have the distance, we have the initial velocity u, we have the final velocity v, we have the acceleration a and the time t. And in this question here, we were told the initial velocity was 2. We know that the final velocity we're going to stop at is 0. We don't know anything about the acceleration. We want to know the time, and we know that the distance travelled is 4. So this is our key information, and one of the SUVAT equations that we're going to look at is S equals u plus v over 2 times t. And if we were to substitute all these values into this equation, that's 4 equals to 2 plus 0 over 2 times t. 2 plus 0 over 2 is 1, so t equals 4. So another algebraic way to use the equation to get the same answer. So let's look at these equations, figure out how they work, and then look at some quick proofs. So it's important to have a sense of how the equations are structured and to try and memorize them. They are on your formula sheet, but the more familiar you are with these, the better. The key thing to know is that you've got these 5 quantities, S, U, V, A, and T, and on this chart, each letter here is crossed out because there are also 5 equations, and each equation excludes one of the quantities. So for example, the first equation doesn't have S in it. So it is A equals V minus U over T, or in another form, V equals U plus AT. The final velocity is the same as the initial velocity plus the acceleration times time, or the acceleration is the change in velocity divided by time. We'll look at a derivation in a moment, but key thing is the equation does not involve s, it involves the other four quantities. For the next one, with a u, we have an equation that connects s, vt, and a. It's s equals vt minus a half at squared. I'm going quite quickly now because I believe all of you should be familiar with these equations. I've seen them at some point in the past. The equation for v, or excluding v, is very similar to the one for u. But this time we build up from u instead of building down from v. So s equals ut plus a half at squared. The fourth equation with no a in it this time is also s equals, and it's the average speed, so u plus v over 2 times the time. And then the last equation, the one we often forget but doesn't include t, is v squared equals u squared plus 2as. So why am I introducing them in the structure? Well, quite often you'll have forgotten one of the equations, you'll be trying to figure out which one it is, and just knowing this structure, knowing there's 5 of them, knowing that each one excludes one of the variables, just helps you stay tidy and get them correct when you're trying to remember them. Now, to think about some proofs, we're just going to use a little bit of geometry really, and we're just going to think about the idea of all of these as straight line segments. So for the first, if I just label them 1, 2, 3, 4, and 5, and I just do a generalized sketch of a velocity time graph where just really general terms, I have constant acceleration, so that's a straight line, and I'm going to have 2 points. I have an initial velocity when t equals 0, and then for some other time I have a final velocity that is v. Now, the proof for the first equation, it really just comes from the idea of y equals mx plus c. If I imagine t varying here and v varying, well, v is equivalent to y. The gradient is the rate of change, that's by definition a. The x value is my t, and my y-intercept is u. So v equals at plus u, or written the other way around, v equals u plus at. That is just the equation of the straight line. Another way to think about it is that by definition the acceleration is the rise over the run, so it is v minus u over t minus 0. So it's v minus u over t, which rearranges to that other form. So either by the definition of the gradient or from y equals mx plus c, we get equation 1. And then equations 2, 3, and 4 we derive just by thinking about different ways to get the area under the curve. So we use area under the graph rather. So we're using the idea that we know the distance travelled is the area under the graph. And if we start from that point, I'm just going to do 3 quick versions of the same graph. So I have u, I have v, and the area is going to be equal to s. For the second equation, so s equals vt minus a half at squared, what we imagine is that to work out the area we want, s here, what we're going to do is work out the area of this large rectangle, and then we're going to subtract that triangle there. So it's the large rectangle, take away the little triangle, and so it is vt for the large rectangle minus the small triangle, which is a half at squared. where does the half at squared come from? Well, we kind of refer back to equation 1 here. From equation 1, v minus u, which is this distance here, v minus u, well, that's equal to at. And if v minus u is equal to at, then this is going to be a half times v minus u times t, for the base times height divided by 2. And so we get this nice neat form without u in it at all. We use exactly the same trick for the second equation, but this time, instead of building down, we build up. So I'm going to first of all work out this small rectangle, and then I'm going to work out the triangle on top. So very similar, but ever so slightly different. The area of the rectangle at the base is u times t, so that's ut, and then this triangle again, well, it is exactly like before, a half times v minus u times t, and then using the first one, that's a half at squared, so the same as before. So my overall equation, s equals ut plus a half at squared. Sorry, one second. So, first one, large rectangle minus small triangle, and then using the first equation just to substitute in for v minus u to get this form of half at squared. Same thing on the second one, but with a smaller rectangle, and then adding on the triangle. And then with the third example, we're going to do something slightly different. We're going to use the trapezium rule. So, for the trapezium, we know a formula for the area. We take the average of the two parallel sides, and then we multiply by the height. So in this case, s equals u plus v over 2, so that's the average of the two parallel sides, and then we times by the height, which is t, so s equals u plus v over 2 times t. That one, nice and easy. That is equation number 4. And for the fifth one, there's no super easy or clean way to do it with a visual definition, but what we can do is we can just combine any two of the other equations really to get a form which eliminates t. Loads of different ways to do it, but maybe my favoured way is if I take equation 4 and I rewrite that, so the one we've just got, to get u plus v. U plus v equals 2s over t. And then if I think about equation 1, well, in equation 1, v minus u equals at. And then if I multiply those two expressions, multiplying the left-hand side, u plus v times v minus u has to equal 2s over t times at. T's cancel on the right, and I get 2as. And on the left-hand side, it's difference of two squares, so I get v squared minus u squared equals 2as, which is kind of neat. So, those are the 5 SUVAT equations with their derivations. And then what we're going to do now is we're just going to see how easy it is to put those into practice. So, first question on the next page. What I want you to do with each one of these is just start out with a little table, S, U, V, A, and T. As soon as you see constant acceleration, you know it's a SUVAT question. So uniform acceleration tells me that this is the case. Draw your little table, fill in the values, it will tell you which equation to use, and then substitute in to get the answer. Have a quick go on this one. Start the video again. I'll show you how I would do it. Okay, so I've spotted that this question is a SUVAT question because it says uniform acceleration. So I write my S, U, V, A, and T, and then I'm going to work out which values I know. So the first thing, starting with S, it says Ben stops after 20 meters, meaning S must be 20, that's for the distance. Then I'm thinking about the initial velocity. Well, yeah, it tells me that the initial velocity is 12, so I know that. For the final velocity, well, it tells me that he's stopping. So if he stops after 20 meters, that means his final velocity is 0. Then in any of these questions, there's going to be 3 quantities I know. There's going to be one that I'm trying to find, and there's going to be one that I don't care about. So I know the first 3 of these. Then looking at the acceleration and time, well, there's no mention of time at all in this question, so I can ignore that, but I am trying to find the acceleration. So what this tells me is I'm looking for the equation that connects S, U, V, A, and that doesn't include T. If I look back to what I did previously, well, the one that doesn't include T is V squared minus U squared equals 2AS. So that's going to be what I use. So on the substituting in for my table, 0 squared minus 20 squared equals 2a times, 0 minus 12 squared, because u is 12, equals 2a times 20. So rearranging, acceleration equals 12 squared, so 144. All divided by 2 times 20, which is 40. So my acceleration is 144 over 40 meters per second, or simplifying a little bit, dividing both by 4, I'm going to get 3 times 12, so 36 over 10 meters per second squared, or dividing by 2 again, 18 over 5 meters per second squared. That's my final answer. So really, really quick, and a very simple form just to use this table, identify the equation, substituting from there. Using exactly that idea, try the one underneath, start the video again when you're ready to go through it. Okay, so this question doesn't explicitly say constant acceleration, but because it's projectile motion, it's an object falling under gravity, we know gravity gives a constant acceleration. So implicitly we know this is SUVAT. So I'm going to put S, U, V, A, and T, do my little table. Really want you to use this technique every time. It's very, very accurate. So a stone is thrown vertically upwards from the top of a cliff, which is 25 meters high. The velocity projection of the stone is 22 meters per second. Find the time it takes to reach the base, correct to 2 decimal places. So starting off with the distance, well, if it starts 25 meters high and we're looking to reach the base of the cliff, that means it must go down to minus 25 meters. We know that it's projected upwards, so vertically upwards with a velocity of 22. We don't know anything about its velocity when it hits the ground, so that's our cross. We know the acceleration is going to be downwards, and it's going to be minus 9.8, which is the value we always use to approximate gravity. And then the time, well, the time is what we're trying to find. So what am I looking for here? I'm looking for the equation that doesn't involve v, so it must be s equals ut plus a half at squared. I'm going to write it out and then substitute in. So minus 25 equals 22t minus 4.9t squared. Rearranging to give myself a quadratic, 4.9t squared minus 22t minus 25 equals 0. If I solve that on my calculator, then I'm going to get solutions. T is minus 0.940 or T equals 5.43, and obviously take the positive solution because it represents the time, so positive solution T equals 5.43 seconds to 2 decimal places written in brackets. So same method again, write the table SUVAT, 3 values you will know numerically, 1 you won't care about, and 1 you're trying to find, tells you which equation to do, and then you substitute them in. Now, final question for today. This one a past exam question, and what I just want you to do is I want you to solve this in 2 different ways. So, to begin with, try and solve it just using calculus without any knowledge or use of the SUVAT, and then underneath I'd like you to use SUVAT, and we'll have a conversation about which is better. So, paper 2, calculate the question, pause the video, have a go. Okay, I'm assuming you've had a go at both of these now. Let me just find it. I have it right here. Here we go. So I've got my 2 solutions, first with calculus. So first thing I did was I defined x to be the displacement from the initial starting position, and then in the question it tells me that the acceleration is constant, which means that x double dot equals a. I've integrated once to get the velocity, which must be a times t plus another constant. I've called it b here, doesn't matter what you call it. And I've substituted in the idea that t equals 0. Then the velocity is 5 from the fact that it says the initial velocity is 5 in the question. So b equals 5. Then the other condition we're given is that after 16 seconds it's moving at 11 meters per second in the opposite direction. So I've put in t equals 16, and this time I've put the velocity to be minus 11, it's going in the opposite direction. So minus 11 equals 16a plus 5, and then rearranging I get a equals minus 1. So this gives me a definitive expression for the velocity as minus t plus 5. And then integrating that again, I get an expression for the displacement, which is minus a half t squared plus 5t plus c. Initially, if we say that that x is the displacement from the starting position, wherever that is, then substituting in c must be 0, meaning that my expression is x equals minus a half t squared plus 5t. And then if I substitute in t equals 16 to finding x of 16, that would be minus a half times 16 squared plus 5 times 16. Figuring it out, I get minus 48. And then the question asks for the distance, so the distance is the magnitude is 48 meters from the initial position. So definitely possible using calculus, but what I like about this question is it shows us how SUVAT, if we know acceleration is constant, can give us a much quicker method often. So I've done my table SUVAT. The initial speed is v5, the velocity is minus 11, the time is 16 seconds, and we're trying to find the distance, and we don't care about the acceleration. So thinking about my equations, I want the one that connects S, U, V, and T. Well, that's the one to do with the average velocity, so S equals V plus U over 2 times time. Substituting in 5 plus minus 11 divided by 2 is minus 6 over 2, so that's minus 3. Minus 3 times 16 is minus 48. So the distance, magnitude of minus 48 meters from the initial position. So a nice example showing really how, first of all, we can always use calculus to work through questions with constant acceleration, but how, if we're smart about it, these SUVAT expressions, these equations that just come from the geometry, from the different ways of finding the area under a straight line, they all give us a much faster and more efficient method. So that's it for today, and obviously that's all the mechanics, the kinematics that I'm asking you to do before I see you again. So what I want from you now is all of 6A and all of 6B exercises completed and corrected before I see you next week. Good luck with it. See you soon.